Hello, Shanmukh. Hello, Aditi.
Hello, sir.
Hello, sir.
So all good? How's your school today? Yeah, sorry, I mean college.
So we have holidays.
Oh, lucky you. Nice. What about you both?
Same, sir. What is?
Yes, sir. It's vacation.
Oh, shoot. Then I should have kept earlier. Then tomorrow shall we have in morning?
Yeah,
Yes,
it's
sir.
fine, sir.
Super. Then because tomorrow evening I have some work, so if it is evening I cannot take. Morning I can take. Yeah, I didn't knew that. Then today morning also I was free. Okay, then let's start. Oh, I'm not sharing. Yeah. Screen share. This one. Because other people's are like not so regular, so we can start. We'll not wait for others. These two are regular. I hope Sanmukh, you will also be regular.
Yes, sir.
Yeah. And good. Not question what we did plus. Oh, one question we did. Today we have full time. We can like finish this chapter and end. So we'll do some system. System, which is executing SHM. Now we'll start with a spring. Then we'll see pendulum, then we'll see YouTube, then some blocks and all that, etc. etc. We'll see. So let's say case one. Now see, this is system in whole like object and its surrounding. We'll consider everything. So if we take first object as two spring, let me draw fixed here, two spring. And one box is hanging on it, or weight of some mass m. So if it is a spring, there will be a spring constant k1. This will be k2. Now here, so if there is a spring, obviously there will be a weight. No, sorry, weight is there, then obviously there will be a stretching movement on the spring. So there will be a force for that. So force kx, F equals to kx that you know already. So let's consider this one also. If it is force constant is combined and it's forming joining here, so it will be k1 plus k2. So let's see here. When it is joined like this in parallel form, connected, parallel, means two spring. Spring having force constant k1 and k2. They're connected here. First one as parallel. That's what we drew here. So k total k will be k1 plus k2. So tension force T equals to 2 pi m by k1 plus k2. than if it is connected in series. K1, K2 in series. 1 by K, it's like a resistance. So T equals to 2 pi M by capital K. So capital K means K1 plus K2, 1 by K1 plus K2. Now see third type. If two masses M1, M2 connected at two ends, like here. So if it is connected like this, and like like if I keep M1 as constant place, if I stretch M2 and release, obviously it will go and bounce back. So for that there will be a diluted mass or reduced mass for that. So if I take here T equals to 2 pi mu by K under root. So your mu is M1 M2 by M1 plus M2. This is mu. Yeah. So mu is this reduced mass. So with this we can say all this, we can have one conclusion, all that, like when this spring length increase, length increase, so spring constant decrease, constant K decrease. So same way, if it is n times, this will become 1 by nth time. So time period is 1 by root, sorry, not 1 by, it's opposite, right? So root n times. It is root times. So length and time period are proportional. So what we said here, what we wrote here, let's conclude again. If length of spring increase and spring constant decrease, like if length become n times, spring constant becomes 1 by n time, and time period will be root n times. Yeah, can you remember this now? Can you remember this one? Yes or no? How many are present today? Yeah, okay. Now, if we divide this spring into n parts, like this is, we just added this way, like first we saw parallel type, then series type, and this two masses are connected with a spring end to end. Then we'll see here, if we divide spring in two, or let's say n only directly, n equal parts. So spring constant k will become nk. So for time period will become 2 pi total mass and k under root. That's it. No big deal here. No big changes here. If it's dividing n times, so they will have each will have some spring constant k because it depends upon material. Have you done writing? Yes. Should I call you by name by name?
So done.
Done? Everyone?
Could you scroll up?
Yes, sir.
The one upper one, case.
Could you scroll up? Into series. Second floor. Yes, sir.
ठीक है, तो चलो नेक्स्ट पार्ट करते हैं. ये कौन सा था? नंबर 1 केस. So now we will see pendulum. Now simple pendulum. So let's draw first pendulum, which is very simple. Right. So pendulum is nothing, just one ball hanging like that. Okay. Okay. So if I take this object and this is your length, and it went here, if I'm just taking a displaced pendulum, object is here, so downward force will be mg. So reverse restoring force mg sine theta, forward force cos theta. That means this should be your theta and this is your length. So x is what? Distance, and theta is your angular displacement and angular displacement. So linear and angular is r theta. So difference between linear and angular is r theta. So this is your simple pendulum, which is having one point mass, which is suspended by weightless. See, we are considering this one as weightless, some string or cord. Okay, we will not consider weight of that string. We just want to discuss about how this pendulum behave, not a string behave. Or what is his name? Mr. Bob. If you remember from your 9th grade, it's Bob. This is string. This is Bob. This one. So linear displacement equals to positional vector into angular displacement. This I think so you remember from your 11th standard. Rotatory and circular motion. So mg sine theta is restoring force, as I said before also, because it's moving back. So how I found out? Because it's moving back. This is moving back or returning force. That is restoring force. So that's here F equals to m d square x by dt square. So can someone tell me how we got this d square x by dt square? From which formula we gave? Yes, anyone? What is d square x by dt square? No one? This is acceleration. How we got acceleration? By this velocity. How we got velocity? By displacement. If displacement is x, so velocity will be dx squared by dt square, sorry, dx by dt, then acceleration will be dv by dt. So v was already like dx by dt. So here d square x by dt square. Second order differentiation. So in this one, this sine angle is very, very small. So we'll consider only theta, just displacement. So restoring force and minus sign, it indicates what? It is opposite direction. So m d square x by dt square equals to minus mg sine theta, means theta. Theta is equals to x by L from this equation. So omega square equals to L. So if we substitute here for simple harmonic motion, t equals to 2 pi by omega, 2 pi by d, 2 pi by omega, 2 pi L by g. Now, thing is here, we need to know how to find this time period of what SHM. So we'll write some steps for that so that you will remember. Whenever we have some numerical, follow the steps. See, initially you follow the steps, then later on no need to, because you will already know now. So for initial stage, you just need to go like every time you need to write and see how it is going. Okay. So how to find S? Okay, let's write here time period. Period of a body undergoing SHM. Let's see here. Have you done this writing, right?
Yes, sir.
Okay. Can you all hear me properly, right? Or is my voice breaking? My voice is not breaking, right?
It's fine, sir.
Okay. So let's say step 1. Now, first thing we need to know, find equilibrium condition. So how to find equilibrium condition or position? By summation of f equals to 0 and summation of tau equals to 0. F means translatory, tau means rotatory. Now, whenever we are displacing the body from original position, okay, so restoring force acting on should be minus fx means kx for translatory. For rotational minus tau k theta for rotatory. So this is what a displaced body from equilibrium, that is x position. So these both are restoring force. One is in angular form, one is in like a translatory form, linear. So then next part is your differentiation part. That's it. Step 3. F equals to ma, so m equals to, sorry, a equals to d square x by dt square. So we will use this one with that. M d square x by dt square equals to minus kx, and m d square x by dt square equals to minus k theta. Then we'll do all the remaining work which is required. Then last step, just substitute as I did before here also. Where is it? While deriving what I did, same thing. Step 4, t equals to 2 pi m by k under root. T equals to 2 pi I by k under root. And I is your moment of inertia. Now, when we are doing this one, if we might use this g value also somewhere if required. So remember that whole system, it's not like depending on g only. It's depending upon their mass, their own masses. Okay. So if the whole system which we discussed right now, or we discuss here, this whole, it's not depending on g value. It's depending upon mass. Main term is your mass. G is not coming everywhere. Mass is coming everywhere. So if it is like a time taken to cover half amplitude from equilibrium position is T by 12. So this was second, what is it? Yeah, simple pendulum. Then let's see here, YouTube. for liquid. Case 3. Liquid in YouTube. So then same thing, we are not going to derive. Excuse me. I'll just draw it, give you small explanation, then we'll write formula. It's not required, derivation is not required. Array mera U. Super. So this is your position. So in this one, we can see here what? YouTube, which is a cross-sectional area, which has A. Area is A. And we are drawing it vertically upward. Both ends are upward. So restoring force equals to minus 2A dg x. X is the liquid displaced or distance of liquid displaced. So if I just drop some liquid inside, okay, if I drop some liquid of mass m and density d. So time period will be equals to 2 pi m by 2a dg. So by this much time, whatever the value those values has, m and d and a, up to that it will be oscillating. This will be, so let's say time period of oscillation. So for this time, this much time, for this much time, it will oscillate. That liquid which is poured in that. See, not this red one. I'm just saying when we drop some liquid in this YouTube, it will be oscillating for this time period. So maybe 1 second, -1, or like 1/4 second, whatever. Or 2 seconds, whatever, doesn't matter. That's none of our problem. That when they give questions, that time we need to just see that how much time it can oscillate, how much the liquid will oscillate to just get into like stable form. Shall I scroll? We'll see another case, chotu case. Let me do the another one. Case number 4. Now we'll drop one liquid. In the liquid, we'll drop some box. Rectangular block in. Array. Now, if this, see, in that also there are so many possibilities. Okay, like, but we'll just see only one. It can be sinking, it can be like floating on the top, or if it is like little bit submerged. We'll see only one case. It's like floating, submerged in the sense floating. So we will see that, okay, only one case. We'll see like how it is behaving in that. So mostly, if we talk about general blocks that are like solid, which is like, what do you say? Yeah, we'll take some iron box. Iron box will sink inside. It's not possible that iron box because of its density. Now, if we talk about this wood, its density is lighter than liquid. Or now that bigger mass also coming here. So if we talk about that, it's like boat, if you remember. So let's draw and see that. This is your will submerge little bit. So if we say it is this much height inside H dash and from above it is at this height H, and this Mr. Liquid has density D, and if we take this one as D dash. So here we are not talking about like what will happen with this liquid and all that. Mechanics of, like, we are not talking mechanics of fluid or solid and that. We are just seeing how much it will oscillate. In this chapter, we are just seeing oscillation and wave created. That is in next chapter. So oscillation, how much it oscillate, that is what it is. So that we just need here time period. We don't need so much things to calculate here. It's very easy. So rectangular block floating. So for that time period is 2 pi under root h dash d dash by g chota d. So if we mention each thing, d dash, d, h, all this. So d dash is what? Density of block. Then this is your liquid. Height of block. And same way, height of liquid block displaced inside the liquid. Case fifth. ठीक है? I guess you're done. So let's go for fifth case. Okay, so here we will see now, we saw some YouTube manometer or spring, then pendulum, then block. Well, let's see here gas. How does gas behave? Vibration of gas system in cylinder. See here we will consider it's frictionless. That piston is frictionless. Because as we know here, our discussion subject is oscillation. So we'll not see a friction. This of area A, of mass M, point B. This is the height H. So time period will be 2 pi mH by AP. So A and P are new term here. For A is area, P is pressure. Pressure exerted by gas. And H, you know already, height on piston. And M is a mass. H is not like Planck's constant, it's just height. Mhm. Case 6. We'll see some small cases. These are also important. Actually, they haven't asked all these cases, but still we should know. Instead of that time deriving and getting the values, this is better you just remember how to get it. Now in this one, if a tunnel is dig in earth, so for that T equals to 2 pi R by G. Now if we take R as a radius of earth and G as gravitation, we'll get almost 84 minutes 36 seconds. It's almost like this value. This is like a diameter type, or we can say like diametrically. So if you say case 7th, so if let's take here ball oscillating in neck of chamber. So there 2 pi by A This is not required, let it be. Yeah, this is required. If a dipole moment P is suspended uniform electric field E, then T equals to 2 pi I by PE. Dipole P is a dipole moment, E is electric field. You just make a note. I'll just be back in like some. Okay. So tomorrow I'm planning to take class at 9:30 a.m. 9 to 10:30.
Okay, sir.
Yeah.
So could you show the case 7?
Yeah. Hey. Yeah. How can it be PE under root? Yeah. What about this? 9:30 to 10:30.
Okay, sir.
Okay, sir.
Okay. Madhusudan?
Yes, sir.
Okay. See, when you're saying okay, that means you should be joining and
Yeah,
no
sir.
skipping. Okay, let's have this calculation. This will be interesting. How we got this value? Let's see. They have written here value, but let's see. Let's try this. Radius of Earth is a 6400 divided by this diameter. Okay, 10 G10 under 8 9 into 2 pi. It will be time consuming, but you tried this. Are we getting the same value? You can check it later. Substitute all the like standard values and check. Is it 86 minutes? Sorry, 84. Okay, then let's go for next part of the chapter. That is oscillation. Oh yeah, that's it. Then we can start tomorrow. We can do exam questions. Yes, then we can finish today. Oscillation. Sorry, yeah, dampen resonance frequency and all that. So give a heading, free, damped, post oscillation. See, name itself, it suggests everything. Free oscillation means free. It's freely moving. Force means forcefully moving. Damp means reducing. So example, let's take here. If I take here pendulum. So actually see, if we consider here everything, all these three will happen here. I'm forcefully oscillating here. I'm just leaving it here. Now I'm releasing. I'm not keep tapping again and again, again and again. I just oscillated once. It will keep oscillating. Now it became free oscillation. Now this free oscillation is slowly reducing. So it became damp oscillation. See, it's damping. So if I draw a graph for damp, it will be damping like this. Are you able to understand what I'm saying? Got the difference between these three? Free, damp, and force. It's very simple. Now free oscillation oscillates on its own without any external influence. So free oscillation, for that it is on natural frequency. So where restoring force equals to minus kx equals to md square x by dt square. So we no need to do differential equation here. It's like fully mathematics side. We'll just write a final form. So if we do differential expression of harmonic motion, it will become d square x by dt square, first order, omega square x equals to 0. Omega is your frequency. So I think you remember this one. This is remember. So if you want to know time period equals to 2 pi by omega naught, that is 2 pi by m, I'm sorry, k here, free we saw. Now let's see here. Damped oscillation. Nothing big here. So every oscillation will become damp only. That is like for sure. Because there cannot be infinite oscillation. So if I take any general idea, like how generally gets damp. If I want to reduce something without any external force, how it will be reduced? How it will be reducing? If I use simple terms here, you can see around everything. Any idea? How to reduce something without any external force? Or our force, we don't want to apply any force. There are some types of frictions available, right? Air friction, ground friction, whatever it is. So here also same thing happening. So this oscillation, it is under influence of frictional force. That is damp oscillation. So let's draw here so that you remember damping means. So here, if you observe that amplitude is decreasing and comes to 0, then force of damping is proportional to negative velocity or speed of the particle. So F equals to minus BV, constant. So M dV by dt equals to minus kx minus b. So this is some damping constant or coefficient. And if we do differential form, so we got d square x by dt square, and here some constant. It's the same thing. dt square plus 2c dx by dt plus omega naught squared x equals to 0. So here 2c, which is b by m. Now which is another one, d is here, or d, what we wrote for b, damping coefficient. Then this c we will take it as damping constant. Then k by m equals to omega naught square. Now in this case, if frequency will be absent here, it will be reducing. So no need to get this so much confusion here. We just need to know all this formula here. And B is your damping coefficient. Then let's finish the last two terms. What are this? What we left? Force oscillation. So that tomorrow only numerical day. force, oscillation. So this will be what we wrote for free without any external force. So it will be under influence of external force or external periodic force. Means we should keep tapping that pendulum, which is going here and coming back. We should keep tapping from here. We should keep tapping so it will get oscillate continuously. That is forcefully happening so that it can maintain all this oscillation what we are doing. So it will not be amplitude. It will not be damped. So even amplitude will be also maintained as it is reaching from here to here. So this amplitude will be maintained. So for this last term, we know resonance. See, this all terms, resonance is just like mixing of some other frequency in like actual form. It just mixing of it. So some external force equals to natural frequency. So from the frequency of external force and natural frequency, when they combine, it forms resonance. In the sense like, yeah, just today only I went for this one music show. So there I saw some, it was like some 6 podiums were there. They were like, I cannot draw it, but they were covered like this, one here, one here, one here, one here, one here, and one here. If I just bang on one place, this music or this sound will go and vibrate, oscillate here and here and here. So they'll mix frequency with this. I'm banging here, banging here, banging here, banging here. All this sound will just oscillate among this one. So if you're in center of it or if you're around it, you will hear huge noise. We are just banging very lightly. Still, it will be resonance. It will create a resonance, same frequency. It's all are of same frequency. So it will be just keep adding on frequency. It will just increase the oscillation. So they will make a more noise. So it will just resonate each other's. It will make it like a very, very large amplitude. So that is what resonance means. Okay, then let's see tomorrow, 9:30 a.m. We'll do all numericals, PYQs. So
Sir,
if
could you show free oscillation? So could you show free oscillation?
free, okay, free oscillation. Yeah.
Done, sir.
Done. Okay. What about others?
Done, sir.
Okay. Okay, guys. See you tomorrow.
Thank you, sir.
Oh, bye-bye.
Okay, sir.
Bye-bye, Madhusudan.
Bye, sir.
Bye.